Introduction. This model is structured, ordered, interrelated, and consistent, which is the signs of a good model. This model explains geologic mysteries. For example, tectonics driving mechanism, Nastapoka Arc in Canada, Bermuda, hotspots in general, Greater Adria and Zealandia microcontinents, relative ages and ages of the Earth's layers, the Mid-Continent Rift in North America Mackenzie Dike Swarm, gravity anomalies, magnetic anomalies, fault system interrelationships such as the New Madrid seismic zone, and even the Theta impact. This model explains all important chronologic geologic events. This model agrees with aspects of the current model, and if not, can explain how the current model came to be. This model is supported and initiated by the results of a 5-year field study in Lower New York, USA, and by an intense analysis of Google Earth. This model is verified and guided by many amazing fractals in North America and around the world. Google Earth. Intense analysis of Google Earth reveals the following about land masses. They are related geologic structures, some of which have broken up. There were 7 land masses or structures. One has disappeared into the Earth. They are presently attracted to a zone between India and Russia. They show details of internal stress and flow-like movement. They show details from amazing fractals within them, such as history of internal stress and flow-like movement, history of high-energy tectonic geologic events, faults that are based on the character of the refolds. Google Earth findings. They're shown in the following. William Pagano's January 2019 YouTube video titled Plate Tectonics, Unraveling the Truth on the William Pagano channel. They're refined and in much greater detail in the PDFs found in the link below. To see all the PDFs, be signed into a Google Drive account, otherwise you only see some of them. The above link is also found at the end of the YouTube video description. Okay, part 2 of this presentation. Part 1 was divided into 1A and 1B, the geochronology of the Earth. Now part 2, other supporting evidence of validity of the model. I'm going to show that the fractals are consistent. The Great Lakes rotational signature mimics model tectonics. Other fractals mimic model tectonics. Geologic mysteries are solved by model tectonics and conditions. Fractals reveal faults, fault systems, and fault interrelationships, which is really in part 3. Just introduced here. Fractals are consistent, as you'll see in the next slides. Okay, in general, I'm going to stick to the point here. Everything else has been covered previously. So this slide shows inner Earth shapes that are nearly identical in 2 different fractals. So the fractal here, that I'm putting a check mark by, this is a fractal in Australia, approximately 875 million years ago. Rodinia has attached to the inner Earth, the beginning of the development of the locking mechanism at the poles. So if you look at the insert at the bottom, there's this fractal from Nova Scotia that's representing about 900 million years ago when Rodinia, with its full cone section and everything, is releasing the chain refold structure of the Earth's moon, what is now the Earth's moon. And the double chain structure was in orbit. It's releasing it. You can see the arms going up, and it's heading towards the inner Earth, which is in blue that I'm circling now. So that inner Earth, when I blow it up here, making an arrow, and showed it on this diagram, stretched it a little bit in one direction, but it's just a stretching. And a lot of these fractals, it depends on your focal point and all, where the fractal sort of is taking a, where there's a picture and you get the fractal from the picture, so to speak, from the photograph. So there could be some distortion anyway, but basically the shape is the same. There's a lot of similarities if you take a look here. So that's why I blew it up. You look at the shape of the yellow outline for the 875 million year old fractal that I'm tracing here with the highlighter. And the one that I blew up here on the right, very, very similar. Okay, here's another slide about how fractals are consistent. There are 6 asteroid impact fractals and 1 Nastapoka arc fractal that demonstrate consistency on many levels. So we look at this, and you can see that these asteroid impact fractals show time phases, such as here. They show different characteristic or dynamic phases. There's full compression here that I'm circling, and this consistency with even the character of the North America refold, of course. Everything's consistent. Every time that these cashew-shaped asteroid impact fractals are shown, they're left of the center line of what was the original equatorial spin axis for the chain structure that got broken up and the individual refolds went all over the place. But it's always left of the center line, and it's always in the top section as it's shown here where I'm circling. So you can see all the similarities here. And this one shows after it had fully rotated counterclockwise. And see where I'm circling here. This is a Nastapoca arc fractal that is shown below, blown up. And the reason it's shown there relative to the large asteroid impact fractal above that had rotated, the reason it's there is because that would indicate the pendulum-like rotation at that point where it is and at that time. So there's this consistency in the character and the phases and everything. And I'm sure I'm missing things, but on many levels, like I said, on many levels, there's this consistency. Okay, this slide talks about how fractals are consistent. It's on many levels. So what we're looking at here is a bunch of fractals that are, there's some inserts from other areas, but you got United States here showing some fractals, and I'll describe what exactly these fractals are in the next presentation. I'll get into the details as to how to locate them and what they represent and all that. I touched on it, but I'll get into greater detail in the next presentation. But based on this text box in blue, I said compare these fractals of early Rodinia. You see that they all have two arms, and the cone section kind of look human-like in the rear end area sometimes. So sometimes they're subdivided on the top cone section. I drew dashed lines in or solid lines, and I just pointed them out. And you also have what's shown here. These are subdivided refold. Those guys above, when they can be subdivided. This is all fractals where things are on different levels and things are subdivided and all that. So what I'm circling now is a fractal from Nova Scotia. It's around 670 million years ago, after the asteroid impact in blue, which you can see below. After that asteroid impact happened, the chain structure of the subdivided refolds there that are like crescent moon shaped, they got the chain got pulled and everything, and tectonics began. So as I discussed previously, the two arms of the Southeast Asia refold, which I'm highlighting here, they got pulled out, and as evidenced by these en echelon structures that I'm circling. So there's a whole dynamic there, and from a tectonic event. And if you look at the white fractal here that I'm circling, there's a sequence of time here. Got the white outline fractal, and the legs are moving in. They go from the white to the red to the blue. And I also put in yellow. There's like this interior Southeast Asia refold thing here. And that's similar to the one below that I was just talking about from the Nova Scotia fractal about 670 million years ago or so. So you can see that bulging in the middle on the yellow one. I'm highlighting it now. That's common to both. And that whole action is shared between the two, and that tectonic sort of action there. Now, all these refolds in general, they have an agenda, so to speak. They're all going somewhere. And again, I'll talk more in detail about that on the next presentation, but that's another thing they have in common. They're looking for like heat sources and going to fault lines and all that. They also could, they form boundaries of whatever it is on like rivers and things. I'm highlighting now, see the upper left. And whether it could be shorelines too, where I'm highlighting on the right now. So there's this consistency. These things are like in the DNA of the land, so to speak. Okay, Fractals are consistent is what we're talking about again on this slide. I've shown this before, but this is showing the form and function of these refold structures, and sort of mimicking what I show on the upper right that I'm circling now, this claw crane machine. And the function of this machine, besides taking your money at amusement parks, is to grasp and pick up these stuffed animals. So it achieves that function by having like a bell-shaped character to it, and you can see that in all these fractals. And that all originated from this fractal here, this insert that I'm circling, that shows early Rodinia in red, and what became the Earth's moon below it. Both chain refold structures, and the stabilized structure was formed when the arms were down of the red structure, and the double chain structure was in orbit around the inner Earth, which is shown in blue at the top that I'm now circling. So once the arms were released, early Rodinia made its journey to the inner Earth, and these fractals are basically showing how the refold structure kept its form with the bell shape, and even included the notch in a lot of these. Circling one of the notches now in this middle diagram here. Next slides show how fractals are consistent with geologic structures and among themselves. Okay, we're talking about how fractals are consistent with geologic structures and among themselves. This fractal that's or fractals that are featured are in Quebec, Canada, and as you can see on the insert, the area of these fractals are shown in the yellow circle. So reading the text box here, in yellow, the refold chain structure fractal that formed the Earth's crust. The fractal is approximately 900 million years old, at least the representation. Note the bell-shaped structure from the previously embracing the crustal refold chain structure of the moon. I discussed that in the previous slide. So there's some basic forces here. If you look at the upper right, this is the pendulum-like rotation from the impact zone. So you're getting that tremendous sweeping motion. And you can see that in the lower right insert. I showed in red, that's the sweeping motion, the pendulum-like sweeping motion. So due to that, you have some little subzones that are, there's some shearing as shown from this SC structure here. And what's going on is I showed the approximate center line of a refold structure. And we put the center line in so it's not cluttering up the diagram. So you can see the character of it as it enters the zone of this SC structure. See the upper part of it here where I'm highlighting? It gets pulled in that direction. So there's consistency there, the geologic structure and the actual structure. Whether this is a fractal or a real structure, I think it's a real one, by the way. So it gets pulled. And now if you look at the fractal below in yellow, like I said, these fractals are always, they have an agenda. They're going somewhere. They're attracted to something. So in this case, the upper cone section is heading somewhere. That's like the leading, the indication that it's heading somewhere. It's leading it in the cone. So I'm circling the area. There's, on this is what I believe is a fractal, not a real structure, but it is, getting curled up in the front here. I think because it's facing the headwinds and it's trying to like apply the brakes, but it's riding right on the back of this thing. It's pretty interesting. And even the top structure that I showed the center line for that fold, even that, if you look at the right end of it, that's curling up too as it's like applying the brakes. So there's that consistency there between the two things shown in blue. Text box here says bulldoze zone in front of the pendulum-like rotation, showing compressional fabric and application of the brakes in the front or leading part of the refold structure fractals. Okay, we're talking about how fractals are consistent with geologic structures and among themselves. So we see in this slide, interesting stuff going on here. The main featured fractal is in the middle of the Google Earth image here, and it's representing what's going on this insert to the right that I'm circling. It's basically supposed to be North America refold that's rotating counterclockwise. So strangely enough, things are coming out of a certain point. There's like a whole city. I wrote there's a complex system of refolds in this entire area, and a lot of them look like baby North Americas, as you see, like the one in green, and I'm highlighting here. So they are coming out and growing out of this arm in red that I'm now highlighting, and sort of showing like a time sequence up to the yellow that matches the insert to the right. And there's a like a baby, what represents the Russia refold here on top, riding on the back. And there's a compression in the back because it's holding on to dear life. And it's moving forward, so this application of the brakes in the front is going on where it's curling up. And where it's rubbing onto the back, it is stretching and pulling, and you get a Boudin in that zone. Interesting stuff. And then eventually this thing loses, and it goes off into the direction of where the attraction is. So miniature refolds are pulled into a suction zone. That's what's going on here with this arrow and everything. Talking about fractals are consistent with geologic structures and among themselves. SC structures and faults. So what you see here is this is in Nunavut, Canada, and shown the green outlined fractal is shown here. See the arrow pointing to it on the insert. I'm circling now. So as I'll discuss later, these guys are pulled into fault areas. They go either parallel or perpendicular to fault areas. They're attracted to the heat because it's like, I'm guessing it's like heat. There's basically a access zone to the center of the Earth where that attraction is. And in this case, there's a SC structure shown in yellow at the top, and it looks like this fractal shown in green looks like it's ready to break its back, getting pulled into a zone here, a fault zone. So there's that consistency. This shear sense for the SC structure is clockwise. I just showed the top section, the arrow for the top section going in that direction. Okay, we're talking about how fractals are consistent with geologic structures and among themselves. Mid-continent rift and a Boudin demonstrating MCR's deformational history. Well, here's the Boudin. Without getting into as much detail as I did on the geochronology of the Earth, you have to refer to that and probably get the PDF and blow it up and study it in more detail. But you can see a Boudin here. Boudins are formed in extensional directions aligned with it, so that direction was this way, and actually both the arms were extended in that direction, both the arms of the MCR, because the area was flowing towards intention, going towards the one arm of the Rodinia refold chain structure, which was embracing the moon at the time. So that caused the tension event. And anyway, once it was released from the other depositional history of that area, which is expressed in this fractal, it you can see the white arrow here that I'm highlighting. It eventually deformed in that direction, and then you see the end of it, which I'm highlighting, has that application of brakes character to it in the direction of movement in the headwinds. So that's the deformation of the structure. Boudin is a structure, essentially. That's an example there. Just in general, the way the character of the deformation of the MCR, the way it looks and what happened to it is based on, of course, where it is. And if you go to the upper right, this is where it is on the original chain structure of Rodinia. Center line of the structure is here. Didn't draw it very straight, but anyway. So there's a reason that based on where the asteroid hit and everything, undergoes this depositional history, which is described in this text box. But there's that consistency there. What you see in the fractal is consistent with what actually happened in real life. It's expressed through the fractal. Something interesting, if you look at the top, it's kind of hard to see this top insert. But the fractal below, the MCR, is shown where I'm highlighting. It's very small there, but it actually transitions in character to what is shown in yellow here. What is shown in yellow is very similar in character of the Lake Superior shape here that I'm now highlighting. That's in the insert. And I believe the Lake Superior shape, looked just like that, just that bulldozed front section to the east there, whatever, is just not shown because of the materials truncated it. It's just covered it up or whatever, but I believe it curls up too like that. Anyway, not so coincidentally, the real MCR, which is mapped out and shown in the right section here where I'm checking, this area is right in Lake Superior, the drag fold like that. So there's this relation between the fractal and reality. The fractals to the left and reality. Kind of interesting. Shows how they're related. Wild stuff. Okay, the next 4 slides show the Great Lakes rotational signature mimics model tectonics. Okay, Great Lakes rotational signature mimics model tectonics. This is slide 1 of 4. The Great Lakes region and evolution of Florida, USA. So Florida is going to be like an indicator, as you'll see. It records rotational history of North America refold, Nova Scotia fractals. Basically, we're looking at the fractals in Nova Scotia. Now, this first image on the left is Earth today. It's Google Earth picture that's marked up with these propagating rotations that all come to a pivot point, and they're bounded by these drag folds, which I discussed previously in the Earth Today section of the previous presentation. Okay, if you look at the large-scale stuff on the right side, you can see there was definitely rotation going on. That's evident in the North America refold, the character of it, how it rotates counterclockwise. And you can see the evidence today by the what's shown in the middle here, the globe of the Earth. It shows the pendulum-like rotation of the impact site. As I'm circling here, it's hard to see that I'm circling it, but it's right in the middle, that yellow area. That shows the impact site. Again, I talked about this before, but the region snapped between New Brunswick, Canada, here, as you see in the lower diagram, and what became Alaska area. It rotated around in a counterclockwise direction, as you see on the upper right where I'm circling. And the resulting subdivision of the northeast area with the subdivision of the North America refold is shown on the lower right here. Great Lakes region is where I'm highlighting there. Okay, we're talking about the Great Lakes rotational signature mimics model tectonics. Slide 2 of 4, we're showing the Great Lakes region and evolution of Florida, USA, records rotational history of the North America refold, Nova Scotia fractals here. Lower left insert is just what we see today, Great Lakes region. Discussed that on the previous slide. You can see the numbered circles are kind of small, but the red one is 1, the blue one is 2, and the magenta one is 3. You're going to see numbered things here on these fractals on the right. You see the same numbers, 1, 2, 3. There's no 3 on the left, but there's a 3 on the right, and there's a 4. The left fractal is 100 million years old, and the right fractal is 30 to 33 million years old. The left fractal, as you see in the inset of this fractal, there's 100 million year old eastern North America subdivided section there, basically from Mexico to up into Canada, and that's before it snapped. Where I'm highlighting here, I couldn't locate the remainder of it, but it's assumed it hasn't snapped. Specifically, that top section hasn't snapped at what became Alaska later, and that counterclockwise rotation occurred. Well, specifically, it's counterclockwise rotation of the arm that ended up near Alaska, but Florida actually rotated clockwise, and the rotational signature that followed is clockwise for the Great Lakes region. So what follows between this fractal on the left and the one on the right that I'm putting a check is that rotational signature. So you can kind of see that. See how the one on the left versus the 1 on the right. So look at each of them, 1, 2, 3, and 4. Again, 3 is missing on the left, but see how they change. The difference is a clockwise rotation of that pivot point. See the pivot point here and the pivot point there on the right. So to look at these text boxes of the first fractal on the left, I say Great Lakes fractal at approximately 100 million years ago, prior to the southern section of the North America refold rotation clockwise toward the Caribbean. Florida went towards the Caribbean, which preceded the snapping of the refold due to tension between New Brunswick, Canada, and Alaska, or Alaska area. The initial rotation, as you see in the 550 million year old fractal in the lower insert, is counterclockwise, at least after that full compression, and then it recompressed, and then it started rotating. The North America refold started rotating counterclockwise. But you can see the labeled number 1 here that I'm circling. That orientation is showing Florida here. It's basically like that, which is parallel to the red number 1 above that I'm pointing to here. So Florida is always an indicator. The orientation specifically of Florida is like an indicator of what's seen on the Great Lakes region, fractals and rotation and everything. So if you look at the right side insert here that I'm checking, that's a 100 million year old fractal. And look at the orientation of Florida now as number 4. Okay, highlighting number 4. And you see up above, number 4 is here. So remember, this is in fact a 100 million year old fractal. The Great Lakes region is shown from this lower insert fractal. So this is the Great Lakes region blown up here on the left side. If we go over to the right side, okay, you can see the Lake Superior bend here and this drag fold from the pendulum-like rotation going this way, and even the Nastapoca arc here, the fractal that I'm circling that shows that pendulum-like rotation, fully rotated to this position, oriented that way. I call it an asteroid impact fractal. It's really a Nastapoca arc fractal. And the drag fold from that pendulum-like rotation is where Lake Superior is, where I'm highlighting. That drag fold, S shape, whatever, in the Lake Superior area. I'm saying in the text boxes, based on the position of the asteroid fractal, this fractal is well after the snapping of the refold due to tension between New Brunswick, Canada, and Alaska area at 100 million years ago. This text box here, Great Lakes rotational mechanics may have started approximately 500 million years ago, although this fractal is estimated to be 30 to 33 million years old. Okay, in this fractal, the overall net rotation is counterclockwise and propagation is to the east-northeast in the orientation of the B line, see in blue above, which I'm highlighting, generally in that direction. The fractal is mimicking the Lake Michigan area. So if you see below, the below left insert, that's kind of what the Lake Michigan area looks like. You see those same numbers, 1, 2, 3, 4, or 1, 2, and 3 anyway in the lower left insert. Okay, so now I'm ready to talk about the differences between the fractal on the left 100 million years ago and the fractal on the right 30 to 33 million years ago. So read this text box below. Okay. Note the changes in the following between the Great Lakes fractal on the left and that on the right. 1. The colored and number propagation lines shape and character as they undergo clockwise rotation, although there is severe simultaneous counterclockwise rotation of the asteroid to the north, and the net movement remains a counterclockwise rotation and east-northeast squeezing of the entire Great Lakes region through the pivot point, as seen in the separate PDF showing the Great Lakes today, which is shown in the lower left insert. So we'll talk about that. So looking at the shape and character of the numbered 1 versus the numbered 1, left versus right, the number 2 versus the number 2, and the number 3 missing on left, but number 4 versus number 4. Just check out that character. I mean, even the number 4, everything is rotated clockwise from the left to the right. As you can see, that pivot point was pulled clockwise. That's essentially what how it shows. And you can still see what's shown on the right fractal. You can still see that today as shown in the actual lineations and all of the Great Lakes, which are shown on the lower left. So back to the text box. Number 2, the shape and character of the landforms through which the colored and numbered lines border and or straddle. So we're going to talk about that now. I mean, even the landforms, for example, you look at between 1 and 2, there's this lake here. And between 1 and 2, there's this lake here. That thing rotated. You got this thing here, looking at the left diagram. You got that on the left. Now you got that over here. And it's amazing. These things are definitely related. So take a look at a zillion examples of that. Take a look at, let's see, what else can we say here? I mean, even this, which is just to the right of 2. See, here I'm looking on the left. I'm circling the lower left area here. See that? Even that is shown here. It's just to the right of number 2 here. Now I'm circling it here. So this thing has moved up about the number 2 line and rotating clockwise. It's like it slipped up, just like the other 2 lakes. They kind of slipped up along the number 2 line as that pivot point was rotated to the right clockwise. So that's an example of what I'm talking about in number 2. So many examples. I just talked about a couple of them. And then related to what I said, number 3, the consistency and order of whether there is water or land on each side of any given colored or number line. And as you progress, in one direction along that line, that's kind of what I'm saying. It goes from land to water to land. That same pattern is repeated. So it's like a duplication between the left and the right. Just the only difference is that rotation. And 4, the nature of the termination of lines 2 and 4 against the land. Even this has rotated. So what I'm saying, if you look at the left, between number 2 and 4 is this straight part of land here that I'm highlighting. So even that has rotated here on the right. You can see that. Even that has rotated clockwise. Okay, we're talking about Great Lakes rotational signature, mimics model tectonics. Specifically here, we have another fractal in Great Lakes 105 to 110 million years ago. Representation. This is slide 3 of 4. Great Lakes region and evolution of Florida, USA records rotational history of the North American reeffold. Nova Scotia fractal of the Great Lakes shown here. We did discuss this lower left insert before, circling it. Remember that in the left, this is 100. I'm going to write it, 100 million year old fractal. Just before it snapped. And one on the right is 30 to 33. Let's write 30. And basically in this main featured fractal, there's an insert of the North America reeffold, a close-up of Florida. It's all the same fractal. And there's like a time sequence that is actually showing a counterclockwise rotation from what's outlined in red here to what's outlined in yellow. So I drew the center line in, which is blue, which kind of mimics number 2 here. See number 2 that I'm highlighting. And it goes to the yellow line, which is more like number 4. Okay. So at that point, at 105 to 110 million years ago, there's still a counterclockwise rotation of Florida from the blue to the yellow, as shown on the insert, or number 2 to number 4, as shown in the middle main featured fractal there. So as I say in the text box, these early Great Lakes area fractals mimic the long axis of Florida at the time of the fractal. At the time of this fractal featured here, Florida is rotating counterclockwise and its long axis is straightening out in the process, basically from number 2 to number 4, as we explained. You notice also the pivot point that I'm circling. Now, interestingly enough, this 105 to 110 million year old fractal, it looks very similar to the 100 million year old fractal on the inset to the left. Now, you notice the only difference really is that more of it is shown. If you were to propagate that lake that's shown in the main fractal here, if you propagate that back to the south and west, it would probably look like just later, which is about 100 million years ago in the lower left insert. So just after 100 million years ago, which is again this left fractal on the insert, just after that is when the Alaska area snapped at New Brunswick area, Canada, and then everything rotated clockwise. And as I said, the Florida direction is kind of indicated in these fractals. So then you have what's on the right side of the lower left insert that we discussed previously. Okay, again, Great Lakes rotational signature mimics model tectonics. This is the fourth of 4 slides for this subject. Great Lakes region USA records rotational history of North America refold Maine USA fractal. We're in Maine. Okay, you can see the insert of, I call it about 60 million years ago, probably closer to 60. Again, just guessing, but discussed this previously. So there's the main fractal there. And I'm pointing to where the Great Lakes in the red arrow is where the Great Lakes region fractal is that's blown up here that we see. So again, we have a lineation that's shown in red. Lake Superior ended up at this dragfold region here that I'm highlighting. I say dragfold from counterclockwise pendulum-like movement of the asteroid impact around area in Canada. And there's that pendulum-like movement right here that I'm highlighting. And again, Lake Superior is here. So you can see these conditions mimicked in the insert, the lower right insert, showing Great Lakes today, those features today that you've seen before. So if you look carefully at it, you can see all these features. These, where I drew the blue lines in here for the featured fractal here, amazingly, they outline just as it looks today. You can see Green Bay, you could see Lake Michigan, State of Michigan, the peninsula, Lake Huron, and Georgian Bay coming together at the pivot point. Pretty amazing stuff. Okay, the next slides show how fractals in general mimic model tectonics. Before we talked about Great Lakes region, but now just in general. Okay, refold fractals mimic model tectonics. Nova Scotia, Canada here. This is slide 1 of 5. All right, first of all, if you look at the insert here, this is the area of the Russia refold, and it shows all the tremendous forces coming in there. We discussed the reasons why. It's basically there's a lot of attraction to the suture where the arm of the Southeast Asia refold anchors down to the inner Earth at the equatorial spin axis, and there may be some access through broken crust, brittle crust on the top sections that make it easier for the attraction to come through the access zones there. So anyway, look at the main featured fractal here in Nova Scotia. Look at the center of it. Looks like the Russia refold here, right? I'm highlighting it. And if you look at the character of it, it's exactly like the one on the insert. Look at the way the left arm is up higher, the right arm is down more. You look at the forces coming in that are shown in blue. Everything wants to come into the center of that Russia refold. So you can see the paths in blue on the left side, and eventually everything's coming up, and if it's too big to make it in, it curls up. So I explain that here in text box. Nova Scotia, fractals demonstrating attraction suction to a distinct zone. The large refolds cannot penetrate the zone and therefore curl up. The small refold at the center of the zone is similar to what the Russia refold looks like today. All right, so we see that. Now I also point out these refolds show a time advancement toward the strongest suction zone. So if you look at this refold that I'm highlighting here, and this one that I'm highlighting here, that's a time advancement as shown by the yellow arrow. And in addition, this one here that I'm highlighting becomes this one here that I'm highlighting. So this is a perfect example of tectonics basically mimicked by the fractals, showing that tremendous force coming into the little guy here, this fractal of what looks like the Russia refold today. Very interesting stuff. Okay, something very interesting here that I'll have to get into more detail later on the next presentation. But refold fractals mimic model tectonics. Northwest USA here, 2 of 5, slide 2 of 5. Okay, so we look, Russia refold structure and suction. Now, that's what we're talking about here. Again, where I'm highlighting now. See this thing outlined in white? Sure looks like the Russia refold, right? Has that same character, basically. Looking at the text boxes, there is a suction fault zone in red that attracts the refold structures, which includes Yellowstone National Park. As I have to talk about it, it's hard not to, but basically the last presentation is about this stuff. But you can see all these guys, all these characters, and there's more than you think. If you look carefully, there's more than you think. They're all heading into the red fault zone. They're either going parallel or perpendicular to it. In this case, mostly perpendicular, and they're getting pulled in. They're like looking for that heat source. They're looking for that access to the inner Earth, so to speak. You know, where that it's hotter and there's that gravitational attraction. What I say here in the black text box, the white refold fractal is similar in character to the Russia refold and appears to be associated with a suction zone, just as the actual Russia refold is. You know, something similar to what we just showed. And there's guys going in there. You can see them getting pulled in this way, you know, right into that zone. So these refold structures are supposed to represent basically 900 million years ago. This is western and northwestern USA. Okay, refold fractals mimic model tectonics. Another example in Nova Scotia. This is the third of 5 slides. Okay, as you see in the text box here, fractals in Nova Scotia, Russia, including Africa refold arm and North America refold dynamics over time. So remember I was saying everything goes in a northwest direction advancement. So that's what's going on here. This blue arrow shows a direction of advancement of time. And this one here that I'm checking is North America about 525 to 550 million years ago, and then it advances over here to where there is a 100 million year old fractal. And we showed the details of both of these, really. So now looking at the featured thing going on here in the center, in red is supposed to be the Russia refold at about 410 million years ago or so. Then it advances to the blue, I'd say 200 to 300 million years ago. And then it advances to the magenta, which is somewhere between 155 million years ago. And you can actually see the one leg curling up. And you can see the outlined in yellow, the arm of the Russia refold, pulling the Russia refold, coddling it, you know, to stabilize it. So it's just like it is as shown in the insert over here on the right. That's Earth Today on Google Earth. So this whole action here with the Russia refold and its rotation direction and everything, and even the arm of the Africa arm, everything's kind of a reversal, sort of an inverse imagery of what's really going on actual conditions in the tectonic history of Earth. And you could see that in the insert. It's actually the, like for example, that the African arm is on the other side of the Russia refold. So there's weird stuff going on with these fractals all the time. Okay, refold fractals mimic model tectonics, Nova Scotia here again, slide 4 of 5. We did talk about this in detail just previously in this presentation, so I won't discuss it again, but I just have it here for completion. It's all related to tectonics. Okay, once again, refold fractals mimic tectonics, USA and Canada here, different fractals. We did discuss this same exact slide before, but just in the context of tectonics was basically the action of the incoiling of the arms of Rodinia here. Well, really the Southeast Asia refold section of Rodinia and how it mimics this tectonic action below here in the insert. So this one is USA here on top, and this is Nova Scotia on the bottom. Okay, these next slides discuss how geologic mysteries are solved by the model tectonics and conditions. Other supporting evidence of the validity of the model. Greater Adria, Microcontinent in Europe. Okay, just reading the text boxes, right side here. Newly discovered continent of Greater Adria that is up to 1,500 kilometers, 930 miles deep. The form of this continent mimics a combination of the following. The form is outlined in red, by the way. 1. Present-day landforms. 2. The suture zone, which is in turn related to present-day landforms and waterforms. And 3. The underlying Africa refold structure that was deformed by the Russia refold collision. The collision moved Greater Adria south and rotated the northern half of it counterclockwise to what is now the western half of the Greater Adria continent. Okay, so you see the Russia refold highlighted or outlined in orange. The big arm of Africa refold is there on the right side. That's the thing that embraced and pulled in the Russia refold, brought it into like south and west and sheared. As you can see, those yellow arrows below sort of sheared the land and crushed that little arm of Africa. I call it outlined in blue. Okay, and then it snapped the Greater Adria microcontinent in half, and it looks like a top hat. See, the left section used to be on top. It fits nicely into the right section. It's because as the Russia refold came down, it snapped it out and pushed it out to the west and everything. So you have the shearing, like I said, during the action of the crushing of the little arm of Africa. You can see that shearing is also evident. So it's kind of like a ductile brittle transition going on here. All right, I talked about this. Russia refold is in orange. Upper left there, although the northern coast of Africa was likely sheared by North America during the Paleozoic, the far northern coast appears to be compressed by the action of Greater Adria around 55 million years ago. That's according to the published study, the geologic literature. Okay, there's a tremendous deformation in the Alps, I'm saying here, because that's all from this crushing of the arm. It's in that vicinity, south of it. Actually, it's right around there. Anyway, volcanic activity in Italy and Sicily, that is to the south, but it's still in the area, so it's all related to this, I'm sure. Greater Adria was likely a land bridge that formed after and above the little arm of Africa, which extended towards the Russia refold 300 million years ago. So as that little arm grew, it took the land with it, and it kind of fostered its the deposition of the sediments and everything, and the migration. Okay, edge, next thing here. Edge of Africa refold has likely been sheared by the movement of North America refold and developed a small arm to the north that was later crushed by the Russia refold as the Russia refold moved to the south and west after it was embraced by the large arm of the Africa refold. The discovery of Greater Adria by others aligns perfectly with this dynamic between the Africa and Russia refolds. So in general, we're just showing Africa and Europe refold dynamics in relationship to volcanic activity. I discussed the relationship to the Alps and the volcanics in Italy and Sicily. I'm also pointing out here, edge of Africa refold, including arms in blue. Noted that before. Greater Adria began to split and rotate to the position shown approximately 55 million years ago. Okay, so now for the details below. As per recent geologic literature, the following chronological events occurred in regards to Greater Adria. 1. 240 million years ago, it broke off what became North Africa. So remember that arm was growing and all, like 300 million years ago. So the Greater Adria was forming, and then it broke off as it continued advancing or whatever. According to my model, William Pagano, WP, this is likely when the little arm of Africa advanced faster towards the suture, in the same general direction as the large arm of Africa. The landmass of Greater Adria was likely a land bridge that began forming 300 million years ago. That's what I was just saying. 2, 120 million years ago, Greater Adria began sinking. I think that was more like, that's what I kind of discovered later here, or what I think. So 105 to 110 million years ago, remember that fractal that was in Maine, where it shows the breakup of Pangea, and it shows the Russia refold like slipped off the back of North America. So just after that, the arm of Africa like went out quickly, and I think during that action of going out quickly around 105, 110 million years ago, it sort of pulled Greater Adria with it and probably pulled it down and out and everything. So that's when it began sinking. 3, 100 to 120 million years ago, Greater Adria smashed into Europe. According to my model, probably closer to 100 million years ago because the arm had to grasp the Russia refold and pull it in. So that's where that collision took place. You know, as it grabbed it, that was the actual collision. And 4, 55 million years ago, it began to take the form as above. According to my model, it took the form as above after it split and rotated from the action of the Russia refold. That's what I was explaining here. So it took it and crushed the arm and sheared everything. Okay, other supporting evidence of the validity of the model: Zealandia, Microcontinent, Pacific Ocean. So this thing takes a journey, and we're going to talk about what happens. So before we move on with that, if you look at the upper diagram here on the top here, the Atlas Mountains formed between 200 and 174 million years ago, as per geologic literature. As per this model, these mountains appear to be related to the formation of Boudins. It's in that area and all that. That rotated counterclockwise and jammed up at the sheared edge of the Africa refold. So that's like over this way was the previous slide, and we saw that there was a counterclockwise rotation of Boudins like this, and they got stuck. They kind of accumulated in this zone over here. You saw it sheared and all that over there. So because of the compression, those Boudins, you know, they got accumulated. So meanwhile, at that time, according to geologic literature, it said Madagascar was connected to India. Now, really, what's going on is there's this land bridge. And again, remember, geologic literature's interpretation of Pangaea doesn't have continent A here, which is here. So everything's closer. By the way, here is Antarctica. This is where Australia is, and this is India here. So you have the two, these two, what do you call them, like arms stretching out to the attraction zone here above. That's caused by Southeast Asia. You got continent A here, the nose, and you got India. So what's going on is as this arm of Africa is advancing this way, it's pulling Southeast Asia arm with it, and it's rotating clockwise, and it's destabilizing the area because the upper brittle crust is getting broken up, and that provides access into the real attraction zone, which is right at the suture to the inner Earth at the equatorial spin axis. But with the breakup, it provides the access to that zone. And as you can see with this this counterclockwise rotation of the system, it's trying to find that access, that suture zone. These individual refolds are responding, and they're looking to get in there. So at 180 million years ago, according to my model, Zealandia, which was being pulled in tension this way and this way, well, because of, I guess, some sudden movement of the Southeast Asia refold or whatever, it finally won out going this way. And there was a little resting position after it zipped out there, talking about continent A, and that resting position is shown in this fractal, this 105 to 110 million year old fractal here, and it's right here. Okay, so eventually, you know, this guy went a little bit further as such, and that's when it did that, you know, that path like this, where it finally went around and went to the next resting position over here, and then finally went into the Mariana Trench here as this thing rotated. I mean, it you know, it came in like that, but this rotated more, I'm sure, the Southeast Asia. So it went through there, which we saw on the other slides. So anyway, what happened with the action of Zealandia? It rotated counterclockwise when 180 million years ago, when the continent A refold backed up quickly. It rotated a little counterclockwise like this. Now, according to geologic literature, it actually, Zealandia pulled off of Antarctica about 100 million years ago. So I think that was when, I'll draw it a little thicker here. I think that was when, you can see in the blue path, when continent A came back around, it probably hooked it over here. It hooked it in this area, and then it dragged it more counterclockwise to its final resting position, which you'll see on the right side diagram, something like this. The reason I know it's in this position, it rotated counterclockwise. If you look at the final position over here, if you see this hook feature here, that is right here. So there's its final resting position is in red. And even in the geochronology slides, I show continent A in this vicinity at around 100 million years ago. So that could be. I mean, you know, it came off of Antarctica about 100 million years ago. It's probably in about this position, and I guess it dragged it over to this position, and then supposedly it came off of Australia around 80 million years ago. So when Zealandia went around the turn, I guess it pulled it off of Australia. And I mean, really, this part here is not technically Australia. It's part of the refold, but that's where you see it to the right. You see where I'm drawing now? That's like, you know, that's in here. So technically, I guess it came off of Australia around 80 million years ago. So if you look at this diagram to the right, it shows Zealandia featured basically where I put the green highlight there. And what I drew in is this is the arm of continent A outlined in purple here. And this is the tail of Antarctica is over here where I'm highlighting, and South America is right here. So you can see, okay, this would be South America right here. I'll do purple for the arm of continent A is like this. And let's see, I'll do it in, I'm doing it in yellow here. This is the tail of Antarctica. You can't see that. Tail of Antarctica is here. So that matches. And there's this tectonic thing going on, which was the advancing arm of continent A. It shows like a displacement there. Okay. And to the right side of the nose of that extending arm of continent A is that land bridge. And you can see that in the original diagram, which I am circling now. Okay. So there you have it. You know, this explains the whole dynamic. It rotates counterclockwise from what's shown in purple on the upper diagram here to the green, or really the red, and then it's dragged over to final position in more or less blue here, which is off of just off of Antarctica, as you see in the upper diagram to the right. Okay, other supporting evidence of the validity of the model: formation of Bermuda off North America and other hotspots. Okay, so Bermuda, we talked about this before, but this is basically some likely the culprit here. So about 100 million years ago, or just after, according to my model, the land snapped on the North America refold, which is outlined in yellow, snapped between New Brunswick, Canada, which I'm highlighting here, and what became Bering Strait area near Alaska here. So it shows the propagation direction and the arrows and everything. And from that tremendous force, apparently, you can see the deformation of North America with the this leg coming down and everything very violently. So it came to the south and the east, or whatever, towards the Caribbean. So I think from that action, there was probably tremendous scraping of the ocean floor, causing the hotspot of Bermuda. Now, I think in general, hotspots are from similar actions. I talked about French Polynesia. There's a hotspot over there. It looks like that was formed when continent A was sweeping around the corner there, working its way to a resting position near Hawaii, which it did the same thing there. It's another hotspot, I think, from the scraping of continent A. So there's And also the Galapagos Islands is from that bulldozed material from the Budins that got plowed through there. So there's this abrasion of the upper crust, probably the oceanic crust that forms these hotspots. It makes like a thinner zone, and the hotspots are the result. Okay, other supporting evidence of validity of the model: the Theta impact and the relative ages of the layers of the Earth. Outer space fractal in Nova Scotia, Canada. And there's also one in Australia here. So this one's like 900 million years old in Nova Scotia. This is like 875 million years old in Australia. Basically, this fractal in Nova Scotia is showing Rodinia in red with the arms going up as it's releasing the moon in green. And it's Rodinia is going to make that journey towards the inner Earth, which is shown in blue. And then that inner Earth is shown in the lower fractal, the 875 million year old fractal, and the subdivided structure of Rodinia is shown as those subdivided colored bordered refold structures that have now attached to the inner Earth. So let's read these text boxes here. Geologic literature states that the inner Earth in blue on that fractal is 1 to 1.3 billion years old. Geologic literature states that the oldest crust of the Earth, the Rodinia chain refold structure in my model, is approximately 4.5 billion years old. The Theta impact, geologic literature states that it was over 4.4 billion years old, based on rock ages though. Okay, text box here, geologic literature, the Theta impact. A large Mars-sized body impacted Earth, and the material ejected off the impact coalesced into the Earth's moon. However, this would require a relatively slow impact. So, according to my model, this slow impact is when Earth's 4.5 billion year old crustal refold structure in red released the Earth's 4.5 billion year old moon refold chain structure in green, and later collided, the actual collision here, collided into what became the 1 to 1.3 billion year old inner Earth, which I showed in blue. So my explanation basically explains why the oldest rock, the oldest material on the Earth is on the outside, and it's younger on the inside. It's only 1 to 1.3 billion years old on the inner Earth, and up to like 4.5 billion years old on the outer Earth. Then there's that great unconformity in which you have the foundational rock, which is like very, very old Precambrian, and then you have a missing time. And apparently it's all over the place. It's not clear in literature if that missing time, that unconformity, the great unconformity, if that's everywhere or not, but apparently it is, according to this model and what's shown. It would make sense that it is, because this model explains the big break in time. All this stuff happened, snowball Earth and everything, and then finally you had more deposition and everything and more rock forming, whether it was the end of the Precambrian or definitely in the Cambrian. So there's that huge break in time that nobody can seem to explain. And the relative ages of the Earth is explained by my model and everything. And the geologic literature says it has to be a slow impact. I'm thinking that it was probably relatively slow when this red refold chain structure, that's Rodinia, went to the inner Earth here, and it didn't blow it apart or anything. It just gently landed on it and tried to stabilize its components on it, and that took some time. It took some shifting around, as we saw, till the Southeast Asia refold shifted down and anchored to the inner Earth. It was something that seemed to be slow. It was doesn't give the impression that it was like particularly violent, because that's why the refold structure did not become disjointed and all that. It stayed together. So just the top part broke off, and it might have even been much earlier, not even necessarily during this event. But anyway, there's a lot of indications it was not a very violent event. Other supporting evidence of validity of the model. The Nastapoka Arc, Canada, slide 1 of 2. Okay, you see, well, first of all, this text box, the Nastipoca arc is the result of pendulum-like rotation of the asteroid impact zone. That's my claim, and I'm also claiming that tectonics are the direct result of the Canadian asteroid impact. So we look at these two published maps here of the what I claim is the asteroid impact site, Hudson Bay in Canada. And the first map on the left is like rock formations that are mapped. The second one on the right is minerals and things like that. Okay, I drew in the red arrows of what I claim is the pendulum-like motion around that asteroid impact center. Basically, all the action got, it came down and then rotated, came down, as I'm showing on each of these, and then rotated, as shown in the red arrow. So by definition here, you see these teeth that I'm circling. That means the side where the action is. It means the side that's not necessarily younger or older, but that's being thrown on top of the side, the opposite side. So being that there's like this bulge here, it means there's a definite propagation of the action advancing in that direction. And not so coincidentally, you see this matches. So I'll show it, look on the other side here. This is the right side, and this is the, well, what's shown here is it shows like the front like this, but it's all related. You see these three shapes here. A formation is or where there's minerals is basically related to conditions. So the conditions that were set up by the actual asteroid impact is directly related to it. This one here, and it's directly related to this. See, it's the same relative size and everything. And that front would be here, that's shown over here. Another thing to note before I get too far ahead, you see this other tooth here? That's pointing to the direction of where the upthrown side is. And I actually show on one of the slides that there's this highly mobile zone of movement that even pulls boudins and everything. There's this discrete pathway that actually ejects the land off this way. So this is the upthrown side here that I'm now highlighting in red. So that makes sense. That's consistent with my findings too. So in a lot of ways, these two, the geologic literature and my findings, agree. So below, to the south of this zone, is Lake Superior, which I claim is a drag fold. It's like this, and it actually gets truncated in the same direction as this. All right, so it's all related. The pendulum-like motion came this way and caused the drag fold of Lake Superior. So the lake itself is like, it's in here and then it gets truncated. All right, so it couldn't quite get past this front here. It didn't have the energy to get past it, so it just stopped. It's sort of like a bulldoze action in a way. And then later there was erosion and all made the lake itself in here. But the action is described by the front, just like it is here. And you can see in both. All right, all related. Okay, other supporting evidence of the validity of the model, the Nastipoca Arc Canada, slide 2 of 2. Nastipoca Arc is the result of pendulum-like rotation of the asteroid impact zone. Saw that on the previous slide. On this one, look at the fractal here in Nova Scotia, the left side. In the yellow circle is what's blown up over here below. This is like a 30 to 33 million-year-old fractal. And you can see that asteroid impact fractal, it has already rotated. So that's at the phase that basically after full counterclockwise rotation, which we have today, is it's expressed through the Nastipoca arc. And that Nastipoca arc, if you look at the lower left diagram, it's right here. It looks tiny there. It's in the right position that it should be there because the energy has been expressed there, and it's going in this direction. And it makes sense that it's there as opposed to here, for example, or over here, for example. It's in the right spot. So it's shown blown up right here, up above. See that? You got the basically the arc shape, and the front, so to speak, that it couldn't get the energy to get past, kind of thing. And actually, if you look at the lower left, that's pretty much this where I'm drawing the line. All right. So you know, the thing's small, but it's basically showing that that front is right over there to the north and east. So in the same fractal that's in the left, those two fractals are the same one, whatever, on the left side. You can see the Nastipoca arc look on the upper right. I'm circling that. There it is. That's the same one that I just showed to the left. And below, or to the south of that, is the Great Lakes rotational signature, which has been propagating to the direction shown from the 1 to 2 to 3 to 4. Incidentally, there was an earlier clockwise rotation that moved the pivot point in a clockwise direction, which is here, the pivot point. But basically, the motion's been counterclockwise and all. So in the lower right, you'll see Boudin, which is a broken up remnant of Boudin, which is on the outside fibers of the rotational zone, which is basically the North American refold. I was talking about that discrete zone that pushed out the, in the previous slide, that pushed out that little area that caused continental drift. So on the insert of this lower right diagram that I'm circling now, in the red is that discrete pathway. So I'm tracing it right now. Goes around the impact zone, pushes out right there, pushes out to the, and makes this, causes continental drift there on that, what I just showed in the purple circle. So it's just a little diagram of North America rotating around the impact site here on the lower left. It's hard to see and all. Then there's this whole thing I'll talk about with the Mackenzie Dyke swarm that has that same pendulum-like rotation and all. So here I'm circling the pendulum-like rotation, and there's the Great Lakes rotational signature here. Okay, so it all seems to be adding up here. Other evidence of validity of the model. The model can explain major gravity anomalies on Earth. Slide 1 of 3. So I drew a diagram of all the refolds and their current character of them in this diagram here. You can see the equatorial spin axis in green, and just notice here there's a north arrow there, and it's going the other way over here. So what I showed here was in the ellipses over here that are shown in red. Those are where the gravity anomalies are. They stand out over here. See, I have the this one right here is the bigger one there, and this one's plenty big too, the other one, and that's shown by the arrow there. The reason they're there is because there's the crust has been busted up there by tectonic events. The one that's, here's the Southeast Asia refold here. The one that's by the closer to the Southeast Asia refold was due to, could be a number of things, but I think it's contributed a lot to the anchor, which goes basically through here to the equatorial spin axis. So it goes to the inner Earth there at the equatorial spin axis below, of course. So I think that anchor moving around and in combination with the arm of the Africa refold twisting the Southeast Asia refold over time, that has broken up the upper brittle zone of crust, which is basically an access zone for the attraction of these individual refolds that want to get in there to the center of the Earth, or at least through the access zones. The ultimate goal is to get to the center of the Earth, where the suture is anchored to. And the other zone over here that I'm now putting in blue, that is apparently from when the arm of Africa quickly went out to catch the refold of Russia right here after it fell off the back of the North America refold around 105 to 110 million years ago, and then it must have fetched it around 100 million years ago or so. So sometime between 105 and 100, when it reached out, it did it, I imagine, so quickly because it was just it had to catch it to stabilize the area. So in the process, it bulldozed or busted up the brittle crust and made a weak spot there. And it's still covering it there, so that that arm is like healing the wound, and it's probably there to stay. Okay, other supporting evidence of validity of the model. The model can explain major gravity anomalies on Earth. Slide 2 of 3. So these are globe fractals in Australia, and they're numbered in chronological order. So this is really a introduction to the next slide. But these fractals of what resemble Rodinia. If you look at the number 1 sequential fractal here, I'm circling these fractals which resemble Rodinia in the fact that there's 2 legs and a cone shape on the top. So where I'm circling them, apparently they're always attracted to heat and everything. And as you'll see on the final presentation, they tend to find the faults because apparently there's heat there or whatever, and they're trying to get in there and everything. So today with that, there's supposed to be a gravity anomaly on around Antarctica, which is the South Pole, and as the locking mechanism is forming, and you get what's closest to a fully developed locking mechanism in number 4. Here's the South Pole here. There's on the next slide, you'll see these fractals are trying to dive into this heat zone over there, and I think that's because there's exposure here. You can see the border here of the Southeast Asia refold right here. It's not fully covering what eventually will cover more area. It'll cover like this zone here, which is not right now. And so I guess there's some exposure to the inner Earth or whatever, and those fractals are feeling the heat, and they're drawn to it. So let's take a look at the next slide. You'll see what I'm talking about. Okay, other supporting evidence of validity of the model. The model can explain major gravity anomalies on Earth. So there is one, like I said, I couldn't get very good information on too much about it for some reason, but there's a gravity anomaly currently in Antarctica, around Antarctica. So that's where the South Pole is, and that's where more or less where this would be over here. So you can see all these characters trying to dive into that zone. And you see there's like exposure there that I call it. See the border of the Southeast Asia refold at this point in time is about right here. So it's not quite covered as it is on this side. You see some exposure there. So these guys are trying to get into that zone. So it's not fully developed stabilized locking mechanism on this fractal yet. And again, the Southeast Asia refold is not really part of the locking mechanism. It's just part of the general stabilization. So, you see these guys rushing in here. It's very interesting. The only ones that are not going right in the zone are the ones that are like far enough away, which are these guys here. You can see I'm circling the tip of the cones. They're not diving into the area as all these other ones are. They're really trying to get into that zone there. Okay, other supporting evidence of validity of the model. The model can verify a major magnetic anomaly on Earth. Okay, if you look at diagrams below, looking at South America and the imagery here that I'm circling, there's a magnetic anomaly there, a negative magnetic anomaly, which is in blue. It's oriented in towards Africa, and positive magnetic anomalies in Africa that I'm circling here in red. Okay, so that lines up with it when they were together. And when the continents were together is Rodinia, which is this upper right diagram. So you can see the red, and I put it in green, but it's supposed to be blue. Anyway, so you see them right here. I'm about to highlight in purple here. So this actually is in the same orientation as the perpendicular element of the Grenville-associated fabric, and it may connect with the one below. Hard to say, but this may not be such a coincidence here, this general lining up with the perpendicular element of the Grenville-associated fabric. I'm just noting this, and there could be something to it. So I'm going to go through this text box here. It describes the history of each of the movements of the Boudins to the best of my knowledge. Okay, here I go. The below negative magnetic anomaly, this is what I talked about, in South America, in blue on right side, when connected to Africa before 180 million years ago when they were together, shows an attraction toward the positive magnetic anomaly in Africa, shown on the right. This positive anomaly, called the Bangui magnetic anomaly, is the red zone that is elongated in the same direction as that of the negative anomaly in South America. This attraction can be seen in the noted red pole of the South America Boudin path below. This pole may have resulted from the initial shoving of the refold structures in the area after the arm of continent A slammed into the southern tail of South America about 350 million years ago, according to my model. When Africa moved slightly as a result, the attractive zone moved, it's probably initiated at least, and resulted in the pole. Again, that pole is like the expanding of South America. It was migrating, unraveling, so to speak. It was rebounding. Although the two Boudins are not seen in the more recent yellow Boudin path, it is likely that they were there in the same position on the yellow Boudin path as that on the older orange Boudin path just before continent A slammed into the southern tail of South America. Evidence of this is the red pole path that went around east of the southern Boudin. Eventually, the pull and the shove from continent A moved the two Boudins out of position. So this is right around 300 million years ago. A newer Boudin path in yellow was created during the struggle as slack was added to the adjacent red Boudin path prior to the launching of the Boudins off the mainland. So it's going to take the path of resistance and take that yellow Boudin path. Before 300 million years ago, probably just before, the two Boudins were likely shoved off the mainland, as seen in the fractal below, in the main fractal. Geologic literature states that South America moved north and slammed into North America at approximately 300 million years ago. These are the two Boudins that were launched off the mainland. So they probably, soon after that 300 million years or so, they quickly rotated counterclockwise and slammed into North America. So it was interpreted as the collision of South America and North America. It's really just the Boudins. The smaller Boudin to the north moved along the newly created yellow path to the breakoff point, rather than moving around the red path where the extra slack developed. It took the path of least resistance. The Boudins likely rested after 300 million years ago in the position just north of the breakaway point, as seen in the fractal below. So all this happened kind of quickly around 300 million years ago with this Boudin launch and then rotation. Then they flipped and moved counterclockwise, as shown in the arrows in the below fractal. At least the yellow Boudin likely ended up above the South America mainland for the first time since its launch. Then at approximately 180 million years ago, there was a bigger movement. A second and larger movement occurred as continent A evacuated and eventually rested in the position shown in the full section of the fractal below. So that's cut off, but you remember that resting position right after the evacuation as shown in the full section of the main fractal. And also Africa moved to the north, a little more, of course, a little more dramatic movements here. North America rotated counterclockwise. This is all a chain reaction, and pulled the Russia refold with it along its arch section, as shown in the full section of the fractal below. Again, that's cut off, doesn't show there. And the Boudins, shown in red and yellow, drifted north to the westerly position, as shown in the below fractal by 510 million years ago. After 100 million years ago, when Alaska and area snapped off New Brunswick, Canada, the Boudins moved south again to the easterly resting position, as shown in the Google Earth image of South America below. Actually, I think they went further down, as you saw in that one fractal. They went onto the mainland, possibly anyway, mainland above South America, and then they bounced back as the North America refold rebounded a bit. Finally, the Boudins rotated counterclockwise after approximately 80 million years ago to their present westerly position, as seen in the Google Earth image of South America below. Okay, so looking at the South America diagram, continent A pushed into South America tail here, probably initiated this red pull to some degree, this unraveling of the and expanding of the South America refold in the red arrow direction. So it's taking that Boudin path and just pulling it there. And the Boudins did, soon after he got launched here, right off the mainland. And then they flipped and everything. So here's the launching position in the insert, and they see, I'm looking at the main fractal here. So they're just off the mainland, hard to see, but that's where I'm highlighting, just off the mainland. Then they flipped quickly, which I'm highlighting now. And that was that collision that was believed to be the collision between South America and North America. So they flipped, and likely at least one of the Boudins ended up above, on top of South America. Okay, then there was the bigger movement of the evacuation of continent A as such in this direction. So that started a chain reaction where Africa moved more, and North America rotated counterclockwise, and the Russia refold was launched off its back and everything. So these movements resulted in the likely drifting of the Boudins to the position that I'm highlighting now, which is the basically the eastern position shown in the South America Google Earth image here. So that's this position more or less. Actually, technically, they ended up there after North America snapped at 100 million years ago, and then they talking about this diagram of the South America. So they ended up there after like really a multi-phase thing. North America snapped at New Brunswick, Canada, and what became Bering Strait, and it shoved the Boudins on top of, or likely on top of South America, and then there was a rebound back up to the north. After the shoving to the south, it rebounded to the north, and that's the position you see here. Okay, and then the Boudins rotated as a pair counterclockwise after approximately 80 million years ago to their present westerly position, as shown here, that I'm now circling. Okay, other supporting evidence of the validity of the model. The model can explain a mid-continent rift in North America. This is slide 1 of 3. You can refer to presentation 1A, where I talk about the geochronology of the Earth. There's further discussion there. Okay, mid-continent rift is approximately 1.1 billion years old. So geologic literature says it was formed 1.16 to 1.09 billion years ago. For simplicity, I'll call it 1.1 billion years ago, and I think that's when it basically ejected off the series of system of refolds was ejected off the large planet around that time. And so just before it was ejected off, there was this arching and refolding on the large planet, and it was all over the place. So Rodinia was like a chain of these refold structures, and I referenced it as a column early in the first presentation. So there's a series of them, and remember that 900 million year old fractal, that's Rodinia shown in red. So it, after it was ejected into space, it latched onto what became the moon later, and then it's in orbit around what was the inner Earth, and that was probably between 1.1 billion years ago and 900 million years ago when the arms are released in that fractal it's showing. So I'd like to show where this MCR is. If you look at the upper right diagram here, this is Rodinia sort of unraveled, and again it's missing that top cone section that I'm highlighting here. That didn't make it to Earth, but the lower did. And Rodinia is more associated with this one leg that I'm highlighting. It's on that side. And here it is that I'm highlighting within that football-shaped structure right here. See that in red? So it's left of the center line, if you want to call it left. Here's the center line of the structure. You have even these legs that are associated with the Southeast Asia refold here. So they're just tucked into the inner Earth, as I discussed, and they're just not shown here. But they're shown in the little diagram on the left. So that asteroid hit left of the center line. If you look just to the north and east of where I just highlighted where the MCR is, so that's where it hit, somewhere in there. And if you look at the published diagram below, it went in a big sweeping motion this way, the momentum of that impact. So it's to the north and east, you can say geographically and whatever, to the north and east of this diagram, published diagram of the MCR. And if you look in the lower diagram showing the asteroid impact in blue and the momentum direction, the direction of the movement to the south and west, the MCR was like right in here where I'm highlighting. So it's just to the south and west of it. So you can see that above where I'm circling. All right. So as I discussed, that momentum where I'm highlighting is going to be affecting the character of the MCR. It's going to get pushed into this physical Grenville front that was formed earlier. And the pieces, as you'll see, are going to like roll over it and everything. So if you look at the diagram to the left, the main featured fractal that I'm checking, you can actually see these phases, which I'll discuss. They go from red to blue to white. They're recorded in this published mapping here. So if you look at the red, actually the white here is shown right there. See where I'm putting the highlight on the published map? Okay, and you can actually see the blue also over here. So that's the blue. Looks like that white is also shown over here. See that? So this diagram on the upper right also shows the Grenville associated fabric, and I'm circling the perpendicular element of it, but I should just note that the one that is near the MCR over here, this Grenville front here, is actually one that is shown in like a crescent moon shape that goes in that semicircular shape like that. I think that's because it found a weak spot in the North America refold. So that's where the fabric went in, and the weak spots are associated with the main fabric of the refolding, which is in that same shape. So you can see all those shapes there and everything. And that does happen where it goes. Could be, it's perpendicular one that does the associated with the actual impact, and then you have this one that's along the fabric or borders or subfabric. So if you look at the main featured fractal, the first event was just after, I'll call it just after 1.1 billion years ago. All the chains ejected, all the refolds ejected like 1.1 billion years ago, more or less. And then the Rodinia chain structure, which had its hat and everything at the time, it latched onto what became the Earth's moon, stabilized it with its two arms, and then ended up in orbit around the what became the inner Earth. And that must have been about 200 million years, from like 1.1 billion to 900 million years ago. And that, in that fractal, you see the arms going up, and it's releasing the moon in that fractal that I always show. Okay, and it shows the two phases of Rodinia and everything, arms closed and arms open. So the first phase shown in red is actually the extensional event when the two arms went around what became the Earth's moon. So there's extension to embrace it and stabilize the double refold chain structure. Okay, so it's evident in that there's like pieces shown. You see the red. It's drawn like where I can see it and everything. I drew some pieces and everything, and they're attached by like what I refer to as string. So those are lineations or whatever that show how these pieces were attached, and it's obvious that they underwent an extension, and that extension is in this direction to the south and west geographically here. All right, and that was from embracing that left arm. Remember in the upper right diagram, I said it's associated with that one arm. I'll call it the left arm. So you'll see that in another diagram coming up in the next slide or two. But that extension was associated with that event, the embracing of the what became the Earth's moon by those arms. So these both went to the southwest in the manner to stabilize that one side, that arm on the one side. Okay. So then there was the release of the moon, like 900 million years ago, that is shown in that fractal where it's just starting to release the moon. And there's other fractals that show like a full spring back of the Rodinia refold, and it's shaped as such. I'm drawing a little sketch here. It's like this super excited kind of version like that. So there's basically a release, tensional release this way. It's supposed to be to the north and east, as I showed. And there's also one going more or less to the north. How do I know that? Well, first of all, the extension released to the north and east. You can see that in the slack developed from highlighting. That's just two examples there. It's kind of like a, the action is evident that it pushed back. There's just the way everything is. The character of it has that signature. Okay. And on the right side, the physical front of the Grenville front, it couldn't get past it, so it kind of just stopped in that manner. Later, the Grenville front must have eroded a little bit because it was able to kind of inch closer to it and roll over it. I'll discuss that in the next phases. But there's also an extension, a release of the extension in this direction, like I was saying. And how do you know that? Well, there's a big kink here, and then it dissipates a smaller one here and a tiny one here, and that's in that direction. If you look carefully, you can see that. So it dissipates to the north. And again, to clarify, Rodinia is associated with this left leg, so it's kind of over here where I'm putting in purple on this diagram in red on the lower left. So the next phase is an extensional phase. Once Rodinia lands on the inner Earth, it stabilizes by forming a locking mechanism between, like, I'm estimating 875 million years ago and maybe up until the asteroid impact in Canada, like 800 or 750 million years ago. So that extension, even according to geologic literature, there's no extension event recorded at this time where the MCR is. So sure enough, you don't even see that here. What you do see, though, is the snapback or release of those locking mechanisms in the blue. Okay, so look at the blue phase. I show the piece-to-piece kind of direction there. There's a little bit of a shrinkage up and moving to the north and east, a little bit less slack, and things are moving up into the northeast, maybe a little bit closer to the that Grenville front, which could have eroded at this point. Okay, so then, and probably soon after this event from the red to the blue, really the blue event, is the white event. Now that's when the momentum of the asteroid impact. Remember, I was discussing the asteroid impact was causing a clockwise rotation, and it was to the north and east of the MCR, and then it swept to the southwest across the top to the north of the MCR. So that momentum pulled everything in a sweeping motion counterclockwise, but only the top half of it. See the white phase there? The lower part was already not able to move because of the front or whatever. But what did happen where it was able to move, this is really interesting. Look at the blue piece where I'm highlighting now. This is like in plan view for one particular piece of this MCR. And then as everything swept counterclockwise, you can see the profile of that piece here where I'm highlighting. So now you see it sideways. It rolled over the front. Okay? and there's more momentum, more movement on the top where I'm highlighting here. I'm highlighting top section here, and there's, well, it's able to, because of whatever dynamic here, it's able to move a little more, but basically it's obvious that there's this sweeping counterclockwise rotation. You can even see a lineation here that I'm highlighting, and it goes all the way around like this swirling kind of counterclockwise thing going on, severe rotation. And also, see this Boudin? First of all, it developed initially with the extension to the south and west, as you can see from the arrow. So that Boudin outlined in white, it also went in a sweeping motion as such. And the headwinds, it's like going in that direction, because if you see the headwinds are affecting that tail, it's like squishing it to shape like this, up against the headwinds. Wow, just looking at this now, the reason maybe that there's that flat part to the white phase on the right side of it, on the upper part where I'm actually highlighting now. See that? Maybe that's flat there because the Grenville front, or like a bulldozed kind of thing associated with it, is flattening it in such a direction. And that's all. Everything's due to the impact, all that momentum. Could be that. And that also kind of fostered this kink here that's in the white phase. It's all speculation, but it's obvious that the momentum of the asteroid impact really rotated things counterclockwise as such, from the blue to the white. Okay, if you look at the upper left diagram here, all these fractals, the one that's featured is shown here where I'm highlighting. It's quite small. It'll transition to what's shown in the yellow over here where I'm highlighting. So that thing kind of mimics Lake Superior, which is here on that insert. Lake Superior hits sort of a front here, where I'm putting that vertical line. But I think Lake Superior would have this curled nose just like that, just like what you see in the yellow. Okay, so it's this drag fold from the pendulum-like rotation of the impact, all right? So there's that transition. It's kind of interesting because, the fractals kind of tell us something. There's like significance to it. So in that transition, and actually where the MCR is found, sure enough, it's the top part of it is found in Lake Superior is there. So that's like right in this area here where I'm putting a check on the right side. So Lake Superior is right in there. So kind of interesting. Okay, other supporting evidence of the validity of the model. The model can explain the mid-continent rift in North America. This is the second of 3 slides. Mid-continent rift is about 1.1 billion years old. One little thing I didn't mention on the first slide, which is in the lower left here. You see this Boudin that I highlighted in purple. That's indicating a, from the blue to the white, that movement. And if you look at a close-up of the Boudin, there's this leading section of the tail, like fighting the headwind that's bent as such. So it's just indicating that sweeping movement that is shown in white that is as such. And the Boudin's there in the first place because it's an extensional environment, that everything was extending to the south and west, as I discussed. One thing you'll notice here is in magenta here, I'm circling. If you look carefully, there's that's actually the center line of another fractal, and that's in I think that's also in Minnesota, not too far away. Anyway, right, yeah, because the fractal I show below is actually right here. So this is a bigger one here, and that outline is in magenta. So you'll see one kink here, major kink in the structure here, and a little kink here. That's 3 of them. So just like before, they get bigger to smaller as you move up, and that's because of that. When the arms of Rodinia released the Earth's moon, there was that compression direction to the north and east as such, and you can see this piece here that I'm highlighting that is oriented the same direction as this, and the pieces got separated here. As you can see, they were attached as such like this. Everything got moved up. That'll be more clear on the next slide. Okay, other supporting evidence of the validity of the model. The model can explain the mid-continent rift. This is the third of 3 slides. Mid-continent rift is about 1.1 billion years old. Okay, so we did discuss this again on the bottom. What I'd like to talk about now is this diagram in magenta. So I put in like the original shape here that I'm circling, and you see that bell shape, just like the because the main structure of Rodinia was grasping the moon like this. You know, it caused like the bell shape and all that, and because of the location of mid-continent rift, which is shown here, you see this yellow fractal that shows the springback action, and I have a little where I'm highlighting now, that's about where the mid-continent rift was, and those yellow arrows are the springback action. So what's causing the kinking is the one arrow here. It's really both movements. I'm circling the 2 arrows. You know, one's kind of going this way to kink this, and the other little kinks that you see, and the other is moving the pieces up, like you can see how they separated here. I talked about that. So you have your kinks, 1, 2, 3 from this movement, and you have your disjointing here, and it kind of feeds into the kinking that's in this direction. So it's exactly what you have here, as I showed in this diagram here. You have that, and you have that. Well, didn't draw it very well. There's 2 directions there. Okay, other supporting evidence of the validity of the model. The model can explain the North America Mackenzie dike swarm. This is slide 1 of 3. So I'm going to read this text box here. Mackenzie dike swarm. The age is approximately 1.27 billion years ago, which is the estimated age of the inner Earth as per this model. And according to geologic literature, the inner Earth is between 1 and 1.3 billion years old. The trend of the igneous rocks follows the dynamic of the adjacent asteroid pendulum-like rotational zone. It has its source in a plug area and rotated as a pendulum. So you can see this plug area igneous source over here. I'm circling it. It is on the border of a refold subzone, and I pointed out where that is to the left. You can see around here. There'll be more details on that on the next slides. But the trend of all these igneous rocks goes in, I'm highlighting here. See this arrow? And that's the same as the trend of the pendulum-like motion of the asteroid impact zone. Okay, other supporting evidence of validity of the model. The model can explain the North America Mackenzie dike swarm. Second slide. You can see the plug area that I just talked about. The eastern border of igneous plug is located along a refold subzone. So that's right here, and you'll see why that exists there. So basically, there's this counterclockwise rotation about the asteroid impact site, as you can see here that I'm circling. I talked about this. So there's actually a discrete path that seems to even pull the Boudins down and control the Boudins, and it also controls this continental drift here. There's like a push off here in this direction. So you'll see more detail on that later, but just very interesting because it has to do with it. It's like a real like a pathway here, a very discrete pathway that I'm now highlighting. It's the red path. There's even SC structures associated with it and everything. Shearing direction structures, SC structures. Okay, other supporting evidence of validity of the model. The model can explain the North America Mackenzie dike swarm, slide 3 of 3. Okay, so that igneous source plug is over here. It's on the border of a subdivision of the North America refold. And what's on borders? Faults. You see an intersection of a bunch of faults in that area that all feed into that source area. And everything is going in like a propagation around the asteroid impact area. At least it's related to that direction, moving around the asteroid impact. And remember here, there's this continental drift here, this push off here. And you had this discrete path that I'm highlighting now. It comes to there's a pinch point here. So all the energy, all the faults come into this point, and it pushes through at the pinch point. And then you have this probably higher energy that's needed to push out the land for continental drift up this way. So that pinch point is actually related to this frontier that that's can't go anymore as the pendulum motion comes this way. It kind of stops, and that's why it squeezed through the one path. So everything feeds into it, and then it squeezed through. So it's just interesting. Everything's all related here. Okay, in the next presentation, we're going to talk more about these faults and fractals, how they work together. Fractals reveal faults, fault systems, and fault interrelationships. See part 3 coming up. Very interesting.